Hello, I am Xiong in Smile Lab, currently advised by Professor Songmin Kim in KAIST. In this talk, I will present our work of SDR receiver using commodity Wi-Fi. This work is done in collaboration with Michigan State University and George Mason University. Recently, wireless devices are explosively increasing and becoming more heterogeneous. This tendency is further enhanced through the emergence of IoT devices such as wearables, home appliances, and smart home devices. Since wireless signals are also increasing, physical layer signal analysis is becoming more beneficial in wireless domain. Physical layer signal analysis is beneficial in various circumstances as follows. In case of network management, we analyze wireless spectrum to minimize interference of signals. For security area, identifying unauthorized RF signals, such as drones, could be done. Collecting IoT signals are also helpful in case of systems like smart farm. For physical signal analysis, software-defined radio is current de facto solution. Software-defined radio, or in short, SDR, is widely considered a de facto solution because SDR can receive ambient signals including standardized and non-standardized signals. Moreover, SDR leverages this received signal data to process various applications such as network management, security, and IoT data collection in a manner of software. Although SDR is able to provide signal analysis functionalities, it is rarely used. That is, the price is expensive, which is hard to be used widely, and they are user-unfriendly as each user has to program through tools like GNU Radio. So, we present SDR-Lite, a new design of using commodity Wi-Fi as a SDR receiver which aims to benefit SDR receiver functionalities to Wi-Fi users. Then, why do we use Wi-Fi to construct SDR receiver system? That is, compared to the SDR receiver, Wi-Fi is much cheaper. For instance, Qualcomm's wireless network interface is only $14. Also, millions of users in worldwide are using Wi-Fi, showing that Wi-Fi is widely deployed in various sectors, such as company, industry, and home. Now, let's figure out which SDR receiver functionalities we can benefit using commercial Wi-Fi devices. Our design called SDR-Lite can do what SDR receiver can do. That is, SDR-Lite can receive ambient signal in the air, and using received data, SDR-Lite can leverage it through software processing, thereby allowing various SDR applications. In the case of the applications, we've done related experiments such as network management, security and privacy protection, and IoT data collection, showing the effectiveness of SDR-Lite. Now, we will go through how SDR-Lite works, starting from the reception of an ambient signal. Let's first see how a typical Wi-Fi packet is received. As we can see, the general Wi-Fi packet consists of header and payload. Given a Wi-Fi packet or signal, a Wi-Fi receiver figures out the length value in the header so that it can decode payload during the time corresponding to length. Then, what if a Wi-Fi packet contains a new header in the payload? If Wi-Fi receiver recognizes as a real header, it starts decoding with the time corresponding to the length value in the new header. In terms of physical layer, This allows Wi-Fi receiver to decode an ambient signal in the air, and we found that a new Wi-Fi header in payload could be generated through signal emulation. Now, let me explain the overall workflow of SDR-Lite. SDR-Lite is triggered by a packet from another commodity Wi-Fi. This Wi-Fi device generates and sends an encapsulating packet that has a short payload holding emulated header. When Wi-Fi sender transmits a packet, SDR-Lite bypasses the original header and receives the emulated header. During a length period in the emulated header, SDR-Lite decodes an ambient signal in a manner of Wi-Fi, thereby yielding bit stream data. Now, our challenges are how can SDR-Lite bypasses the original header, and how can we emulate a new header? Let's first see how SDR-Lite can bypass the original header. We define the packet containing emulated header as an encapsulating packet. The encapsulating packet occupies 40 MHz bandwidth, which enables emulation with high degree of freedom. Then using left 20 MHz bandwidth, a new header can be emulated. We could easily find that the center frequency of the encapsulating packet and emulated header is different. Therefore, if we set SDR-Lite's channel as 20 MHz center frequency, SDR-Lite could not decode the original header, thereby bypasses it and receives an emulated header. Thus, we showed that high precision of emulation while bypassing the original header could be achieved. Next, let's figure out how emulation is done in more detail. As seen in the previous slide, encapsulating packet contains an emulated header in the payload. Encapsulating packet consists of 40 MHz bandwidth OFDM structure having subcarriers starting from -58 to 58. We use payload for emulating a new header by using subcarriers -55 to -3. The emulated header structure is shown as this following Wi-Fi standard. Since we use payload to emulate a new header, we need to check discrepancy of payload and header structure. To emulate a header, we use payload since payload has high degree of freedom for emulation. However, payload and header has some different structure. In point of view of symbol format, emulated header has this kind of format, including short, long symbols, by, and mag, while payload consists of 4 microsecond symbols. In case of the modulation, header uses BPSK or 16 QAM, while payload uses 64 QAM. Now, let's see how emulating a header could be done under these discrepancies, starting from symbol format. We take 5 short symbols as an example. Figure shows basic structure of payload symbol that belongs to encapsulating packet and 5 short symbols. Each payload symbol consists of 3.2 microsecond OFDM signal and prepended with a 0.8 microsecond cyclic prefix, or in short, CP, which is a copy of the last 0.8 microsecond of payload symbol. Under this discrepancy, if we let 3.2 microsecond payload symbol to emulate 4 short symbols, CP automatically copies short symbol. Thus, short symbol emulation is doable. Now, we will show how to emulate header signal in terms of modulation, which is closely related with signal shape. This constellation map represents the modulation of Wi-Fi and determines how Wi-Fi signal looks like. The payload of the encapsulating packet can have one of 64 black dot points, and long symbol can have one of 2 red points as shown. We take this long symbol as an example of constellation mapping. Since the Wi-Fi signal shape is determined by choosing constellation points, selecting the nearest point to long symbol is the best. Given the fact that each constellation points are one-to-one mapped with 6 bits, we found that controlling 4 bits out of 6 bits is doable while considering the Wi-Fi code rate. Due to the gray coding's property, where nearest points differ with only 1 bit, if we determine 4 bits out of 6 bits, then constellation points are automatically set to be nearest 4 points within a square box. For instance, if we fix first, second, fifth, and sixth bits as 1010, then the constellation points will be one of these 4 points. And this feature allows us to emulate header in optimal, considering Wi-Fi's code rate. Based on this emulation technique, we can successfully generate an emulated header. Now, given the emulated header, SDR-Lite receives an emulated header plus an ambient signal, thereby outputs bitstream data following the Wi-Fi's decoding procedure. Then, we want to know how can SDR-Lite reconstruct an ambient signal from bitstream data and enables various applications. The answer will be shown in software processing part. Until this, we've seen that how SDR-Lite could receive an ambient signal through header emulation of the encapsulating packet. Next, based on the reception of the ambient signal, we describe software processing and applications of SDR-Lite. When SDR-Lite receives an emulated header, it starts decoding an ambient signal following Wi-Fi standards. The ambient signal is sampled and from the 0.8 microsecond signal for each 4 microsecond is deleted due to the CP removal function. These samples pass IFT function, convolutional decoder, and outputs decoded bits due to the basic decoding procedure of Wi-Fi. So our question is how to reconstruct the ambient signal. The answer is simple. We insert decoded bitstream data following the Wi-Fi encoding process. That is, decoded bits go through convolutional encoder, FFT, and CP attachment function. Therefore, we can reconstruct an ambient signal using decoded payload bits. This is an example of in-phase comparing a reconstructed ZigBee signal to ideal one. As we can see, reconstructed signal closely mimics the original ambient signal. However, due to the Wi-Fi's constrained degree of freedom, it is natural that some errors occurs. For instance, CP removal function makes error on front part of signal. Also, FFT function generates boundary errors which enforces reconstructed signals to be cyclic. And convolutional encoder let reconstructed signal to have errors as shown in the figure. To mitigate the errors, we used phase compensation through cross-correlation technique and time domain filtering technique. For details, please refer to our paper. Now, leveraging the reconstructed signal, let's focus on applications of SDR-Lite, starting from RF fingerprinting. Using SDR-Lite, we could successfully reconstruct ambient signals where reconstructed signal closely approximate the originals. Leveraging reconstructed signal, we classify signals using machine learning techniques such as support vector machine or deep neural network. Therefore, SDR-Lite can do device detection and classification. Moreover, the reconstructed signals could be directly used for spectrum monitoring. Taking reconstructed ambient signal, we use FFT function. Then, we could obtain the amplitude of each frequency component through Constellation point. Since we know the amplitude per each frequency component, we could generate a waterfall plot from SDR-Lite, as seen in USRP, but with low precision. Thus, SDR-Lite can monitor wireless spectrum. Lastly, SDR-Lite can decode ZigBee signals. SDR-Lite receives a ZigBee signal and reconstructs the ZigBee signal. As we've seen before, reconstructed signal has some errors. Nevertheless, due to the robustness of ZigBee decoding, SDR-Lite could decode ZigBee symbols. Here's our experimental setting. For SDR-Lite, we use AR9380, Alpha, D-Link, which are commodity WNIC, and USRP. For ambient signals, we use various drones, smartphones, and router for device classification and detection. We use TICC2650, which is a multi-standard chip. Also, we use RC card and microwave for non-standard signal. Before showing experimental results, let me show you how SDR-Lite works in action. In this video, we use drone as an ambient signal. We first turn off SDR-Lite. When SDR-Lite is turned off, obviously no packets are received. Next, we turn on SDR-Lite. When we turn on SDR-Lite, it successfully receives packets which contains drone signal. We can obtain decoded bitstream data which follows Wi-Fi standard. Using this received bit, we can reconstruct the drone signal and waterfall plot as shown. This result could be used for unauthorized UAV detection. Now, let's talk about the experimental result, starting from drone detection. For drone detection, we use 3 drones for the experiment. This figure shows the reconstructed signals by SDR-Lite. We could find out that Mavic Pro uses sinusoidal-like signal and 3DR Solo uses more complicated signal. Using this reconstructed drone signal, we experimented drone detection comparing SDR-Lite to USRP, which is general SDR. We used 1D CNN architecture for machine learning technique. The figure shows that SDR-Lite could detect drones with 98%, while USRP achieves 98.2%, showing that SDR-Lite can detect drones with high reliability. Next, we analyze standardized signals using SDR-Lite, such as BLE and ZigBee. We can find out that BLE and ZigBee signal are well captured with different channels. We also analyze non-standardized signals using SDR-Lite, such as RC card and microwave. We can find out that RC card signal has narrow bandwidth, while microwave has more wide bandwidth. And microwave uses non-continuous RF signal in time domain, unlike RC card. Therefore, SDR-Lite can monitor the RF spectrum, including standardized and non-standardized signal. The last is the ZigBee decoding. For detailed analysis, we use USRP to send recorded emulated header and ZigBee signal. And SDR-Lite are used to reconstruct and decode the ZigBee signal with different locations of A, B, and C. As a result, SDR-Lite is able to decode ZigBee with symbol error rate lower than 8% in each location. If we use multiple SDR-Lite and use majority voting for ZigBee decoding, symbol error rate with 0.56% could be achieved. Thus, SDR-Lite enables highly reliable ZigBee decoding. Finally, let me summarize our work. In this work, we proposed the first zero-cost software-only SDR receiver called SDR-Lite. SDR-Lite can receive an ambient signal through an emulated header and reconstruct an ambient signal. As demonstrated with various experiments, we showed effectiveness of SDR-Lite through three major applications such as unauthorized UAV detection, network management, and IoT mobile data collection. Finally, SDR-Lite spreads the blessing of SDR receiver to billions of Wi-Fi devices and households to enhance our everyday life. Thank you for listening.